Very honored and very pleased to work with our partner for this forum. I'm going to share the two presentations and later on Graham will take over for the panel discussion. I think technology is very important for us to develop population genomics and also precision medicine, and we are very happy to be able to adopt this new generation sequencing technology. And we have been discussing with Illumina, and they are very helpful to help Taiwan to do our capacity here to do the large-scale work. So without further ado, I will first ask Dr. Donavan Cheng. Donavan is originally from Singapore. He studied in Toronto, Johns Hopkins, and working in New York, and he has been with Illumina. So, Donavan, please.
Good afternoon, everyone, and on behalf of Illumina, thank you to Peter, Dr. Tsai, President Liang, Vice President Situ, for including us as a partner and co-organizing this event with us. My name is Donavan Cheng. I'm part of a group in Illumina that's called Population Genomics. Many of you may know of Illumina as a provider of sequencing instruments, array instruments, and so on. But we are also extremely vested in the success of the strategic initiatives worldwide, the healthcare systems that are incorporating genomics into routine practice. And our group is basically responsible for working with these large-scale initiatives globally. So for today's talk, I'm going to touch on the operational concerns and challenges of implementing a learning health system that you guys have heard about in the previous presentations, with a focus on informatics because that is the background. So this slide is just to show that there are an increasing number of national population genomics initiatives globally. And this is really spurred by the relative ease of doing genome sequencing with de novo in recent years. And I think a theme that has come about in previous talks during this meeting is you really do need large numbers of local populations to really characterize the effects of genome variation within different geographies. And here's just a kind of simplistic statistical analysis in order to kind of walk down the number of genomes that are needed to really enable rare disease allele discovery and novel gene-environment interactions. And it's unlikely that any given health system is able to amass a large enough and rich enough genomic data asset on its own. So we see an opportunity here not just to enable the success of any given one population genomics initiative, but really kind of work with all of them so that they progress in a coordinated manner and they're able to basically have reduce technical barriers to enable coordinated data sharing across health systems. We talked a lot about the learning health system, and this is a graphic that shows up in quite a few talks around population genomics. And one of the previous speakers talked about the lifetime value of a genome in terms of healthcare. And I think this really speaks to that because during routine practice, when a person gets assayed for their genome, there's actually a lot of value in actually managing that data, placing it in an aggregated data asset, providing the data management infrastructure so that you can basically tap into this, mine it, and produce insights that can then prospectively inform the next patient's diagnosis. And the reason why I want to bring this up is, underneath this paradigm lies a number of operational challenges. And here are just some that are listed on this slide. And I've divided this in terms of the left hemisphere, which is around implementing a clinical accredited workflow and a testing paradigm in the health system. And the right side, it's really around kind of managing that aggregated genome data aspect. So in terms of the left side, there are many different considerations, such as being able to operate at scale, meeting accreditation requirements, getting back to patients with appropriate turnaround time, and the use of standards. And really, this whole process requires something that is versionable, locked down, and automatable. And it also requires a lot of expertise and experience. And that's why I put up the graphic on the right, which is really speaking to, and I like this, it's kind of finding the causative variant in the haystack of all the genomic variants, the millions of genomic variants that can come out of the WGS test. And really to do this in a way that is scalable, you need an automatable, you really do need to automate the process of genome interpretation. And so that's something that I'll touch on in the next few slides. In terms of the right side, we heard from Peter around efforts in GA4GH to set up the standards for data sharing. But in addition to those standards, there's a lot of other concerns in terms of normalizing the data, making sure that things are kind of matched to the same ontologies. You know, something that's called breast cancer and SNOMED is probably analogous to something else in HPO. Being able to do that in a way that is computable, that lends itself well to downstream analysis, being able to set up the informatics infrastructure so that the data remains resident and queries are then federated out, being able to link the genomic information to the phenotypes and structured health information from the EHRs. All these are considerations that really need to be put in place in order to realize a fully functional and connected learning health system. The reasons why I'm bringing this up is Illumina, in addition to being a provider of kind of instruments and tools, we work with large-scale population genomics initiatives to help them take down some of these barriers, take down some of these, address some of these concerns. And during today's talk, I'm going to provide you with two anecdotes. One, our experience with Genomics England that we've heard of quite a few times during the past 2 days, as well as another anecdote working with Sick Kids Hospital in Toronto, Canada. And then finally, I'll leave you with some of the preliminary findings we've had from our experience working with some of the data being generated by the Taiwanese actually. So in terms of Genomics England and the first story, I won't need to go into this too much because you've heard from about the 100,000 Genomes project by multiple speakers here over the past 2 days. Suffice it to say that they've been very successful. They've analyzed 100,000 genomes and they're moving on to actually commissioning whole genomes as part of routine testing in the National Health Service. But if you took a step back and looked at the history of this, back in 2016, it wasn't always, a smooth running machine. So we worked with Genomics England for various things. And one of the things that we've established with them was this Bioinformatics and Clinical Interpretation Partnership, which is the BCIP. And where this really fit in the overall Genomics England workflow, if you look at it kind of from 12 o'clock, and then clockwise, is really downstream in the process of facilitating interpretation and facilitating these molecular tumor boards or molecular genomics boards, multidisciplinary teams that you heard about in previous talks from other speakers. Just to go through this from kind of 12 o'clock and then clockwise, starting from sample recruitment, Illumina has actually participated in the job project by setting up a lab called Illumina Lab Services in Kingston. So this is a centralized sequencing facility. The different biosamples that are gathered at Milton Keynes get sent there. There's extraction onto, going through high-seq workflows for rare disease as well as oncology. We've helped them kind of debug their formalin FFPE workflow, help them move over to a fresh frozen workflow for cancer, for example. All of that within a ISO 15189 accredited framework. And then the informatics partnerships comes downstream in terms of interpretation, collaborative review, really facilitating these multidisciplinary teams. And the challenge that they faced back then was they had 13 different genomic medicine centers that were distributed around the country, all of whom were sourcing samples into this 100,000 genomes project. But each center being geographically distant from each other and also maybe having different specializations and different disease areas. So the sequencing was centralized, but the interpretation required participation from different groups that weren't kind of co-located together. So they needed an informatics tool to basically facilitate these types of virtual multidisciplinary teams where they can actually perform interactive review, ask questions, pass a case from maybe one GMC to another GMC, and may have a specialization for this particular set of phenotypes, have a knowledge base to really record all of that, manage the curations that came out of it. And this became a tool that was called base-based variant interpreter. We also built another tool as part of this partnership called Caselog, which is basically, if you look at it, two boxes over here, a large data structure that basically crosses between variants as well as phenotype terms to enable large-scale statistical queries, joint queries of genotype and phenotype. So basically ask questions like, show me all the loss of function variants in this particular gene for the following phenotypes, help me calculate burden statistics, chi-square tests, et cetera, et cetera. And being able to do this for case control types of questions, or flipping it around instead of GWAS doing GWAS. I'm not going to touch on this very much, but just suffice it to say that variant interpreter is an online review portal. It's very similar to other kind of variant interpretation software. We currently have about 10,000 whole cancer genomes loaded in this to support the 100,000 Genomes project and moving into the Genomic Medicine Service in the NHS. And this is the largest number of kind of simultaneous loaded whole genomes in cancer that I know of. And the beauty behind this system is that despite having tens of thousands of whole genomes loaded, those queries are all very rapid. And so it's not like scaling from hundreds to thousands to 10,000s, there's any degradation in the query performance and the ability to interactively review these genomes. Here are just some examples of where this is useful. So Genomics England issued static reports for their cancer genomes in addition to providing a dynamic review software for these multidisciplinary teams. And the downside with static reports is you usually have cutoffs. It's like the variant frequency has to be larger than 5%. It has to be less than 1% 1,000 genomes, et cetera, et cetera. You have these hard-coded fixed cutoffs. And inevitably, these cutoffs may lead to things that are missed. And so during these molecular tumor boards, they sit down and they say, given the following tumor type, I think there's something here. And so what they did for this particular case was look in BRAF. And they identified a novel fusion here that wasn't into traditional BRAF fusion. It was a zinc finger BRAF fusion. And they were only able to do this by interactively reviewing this, going into the visualization, clicking into this, and examining the breakpoints. And then they noticed that this was actually missed because the hard filters that were built into the static reports, this had just barely failed one of those cutoffs. And the end result of this is the patient's been placed on MEK inhibitor therapy, which is downstream of BRAF, and that patient looks like he's responding. Here's another example of this, where there was a novel ALK fusion, and the software basically identified these breakpoints over here, and you can see over here with the changes in coverage, there's a dip here indicating there is a structural rearrangement, and then in terms of the allele frequencies, there's a change in overall allelic balance in this region, suggesting that there is a large-scale variant that happened. This was initially misdiagnosed as a GBM, and this was an ALK fusion. That's not a characteristic ALK fusion. And just to, I think, one of the earlier speakers' points, the reason why you would do genome sequencing is because sometimes the breakpoints are actually not in characteristic places. This one happens to be in the introns. And genome sequencing is able to identify these things, whereas targeted enrichment approaches like exome sequencing might miss this. And there are, of course, therapies available for ALK fusions. This is a crizotinib case. So, this is just an example of where through the molecular tumor board and kind of going one step deeper into the case through interactive review, actionable variants were actually identified. With Case Log, this is something that we're developing still with Genomics England, and the use case over here is not just for GEL to enable the different researchers as well as the clinicians and the GMCs to query the data. It's now been morphed into something that's much more global, adhering to some of the standards being developed by GA4GH to allow federation. So not only are you able to accept queries from a global site, you're now able to accept queries from other places, compute this, summarize this, and then return it to the requesting sites without actually moving the underlying data. And the part of this that's really that we've enabled is kind of the infrastructure piece to enable sub-second queries up to 100,000 genomes in terms of overall capacity. Now moving on to the second story, Illumina does have a portfolio of different informatics capabilities that we can use to kind of empower and enable large-scale sequencing initiatives. One of them that I'd like to touch on is really the Dragen tool that came to us via the Edico acquisition. And so for those of you who don't know, this is a hardware accelerated genome analysis technology. So FPGA stands for field programmable gate arrays. And this tool over here can be available both on the cloud as well as on premise. And the second story that I'm going to talk to you about is really through our collaboration with SickKids in Toronto. And so this is a hospital that's been kind of asked by the province of Ontario to develop a whole genome clinical test on behalf of the various clinics in Ontario. They currently have an HPC cluster, but their current workflows on this HPC cluster roughly takes them about a day, or 8 hours to a day to basically align a genome. And there's limited throughput of this cluster to basically accomplish the turnaround times that they want. They also had questions to us in terms of the recommended sequence coverage per germline whole genome. And so we worked with them to basically benchmark and improve the Dragen pipeline. So through our work with them, we've basically optimized Dragen for the GRC H38 version of the genome to make it much smarter handling decoy sequences and also handling reference minor alleles. And this is some of the data that the SickKids group generated comparing Dragen versus GATK 4.0 on the NIST dataset NA12878. And what you're looking at over here, different colored bars. In blue is the Dragen results in terms of the total error rate for this truth set. And then in the colored bars, and maybe just pay attention to the yellow, is these are the hard filtered quality, quote-unquote, quality SNPs called by GATK4. And moving from left to right, you can see a increase in coverage. So this is basically a computational downsampling or titration on the overall coverage value. And what you see over here is, given a lower amount of coverage, the error rate for Dragen is still comparatively lower than GATK when GATK is given a higher amount of sequence coverage for the same region. So really, we've optimized it to the point where we're able to achieve similar performance for less sequencing coverage per region. And this trend holds not just for point mutations, but also for INDELS. Similar type of plot. And maybe here's just like, the ROC curves, and this is a more dramatic one for small INDELS. And you can see that all of the lines over here correspond to the Dragen, and really you want upwards and to the left when it comes to receiver operating curve. And so regardless of the coverage, this typically optimize the Dragen pipeline to be much more performant than that for GATK. And this is on top of reducing the turnaround time for running the analysis. It takes about half an hour as opposed to a full day. And I think this is really interesting and really cool because SIGKITS has other truth sets in addition to what's available through the Precision FDA. So they ran this on a Han Chinese trio as well as an Ashkenazi trio. And please don't pay attention or try to read the numbers, but just suffice it to say that it doesn't change. So that kind of acceleration and increase in performance is consistent regardless of population background. And maybe just to conclude, we've worked with NHRI for about maybe less than a year. We first interacted with Peter in earnest starting in December. And he came to us and he said, well, I've already started doing genome sequencing in my facility. And is there something that we can do together in terms of informatics? And so as a pilot, we actually helped them load 100 genomes into our informatics stack in Amazon Sydney. This consisted of about 50 cancer samples, so 50 tumor normal pairs, liver cancer as well as bladder cancer, as well as 50 probands, half of whom have developmental delay and half of whom have cerebellar ataxia. So the numbers are very limited. This is just a proof of concept to see if we could actually load it and see if anything came out of it. We loaded the samples within less than 2 weeks. So it was actually really a very smooth process in terms of getting this loaded and then passed through the entire pipeline. The data actually looks really nice. So here's some of the liver cancer samples, very clean, fresh frozen. These are some of the plots that came out of it. They look just as good as any that I could have, thought that this was from one of the Genomics samples. This particular case happened to have a P53 hotspot mutation as well as a TSC2 loss of function mutation and a recurrent mutation in CDKN2A in pancreatic cancer, which is actually not that far away from where the liver is located. So there are already some very biologically relevant mutations just from this very simple proof of concept of just putting the samples through our pipeline. We use the case log method to kind of just load some samples in here. And granted, it's less than 50, but we already identified some hotspots. If we load more, I'm pretty sure we'll find more interesting recurrent trends. Beta-catenin, S45P is a known cancer hotspot. If you look it up in Cosmic, it's recurrent in liver cancer. And so here is just kind of validation, sanity checks that these things actually make sense for this data. And this is a little bit of late-breaking stuff, but Illumina also has a research and technology development group that is investing in artificial intelligence, deep learning assisted interpretation technologies. So when it comes to automating interpretation and helping with that, we're actually making some strides to kind of push that for the entire community. And one of the algorithms that we've developed and published on is the ability to use artificial intelligence, deep learning, to learn about local genome structure, to predict cryptic splice sites that may not be close to the exon-intron boundary. And so this is a paper that was published in Cell just this past year, actually in January. And it's a 32-layer residual neural network that has been trained on various truth data for splice mutations and is able to predict cryptic splice sites deep into the introns of genes where you might not have looked earlier. We compared this to other algorithms like MEX, Antiscan, and NNSplice, and found that their ability to recover the known splice sites for some well-known genes like CFTR was roughly around 20%, whereas we could do this with like close to 100% accuracy. Some of these splice sites were further validated through collaborations in terms of RNA-seq to just basically make sure that in cases where a strong splice site was predicted, there was actually an A-variant transcript that was produced. And so what we did was we took the developmental delay samples through this just to see if there were high confidence hits. Just because of the limits of time, we limited our search to about 1,000 genes for intellectual disability. We looked at regions that were adjacent to exons to about 50 base pairs. We also looked at promoters. And we had at our disposal the 50 matched normals from the liver cancers, which could serve as a vague control set. And I'm not saying that we have anything that's statistically significant here because the numbers are very, very small, but we have some interesting findings. I mean, we have some sites that are in these intellectual disability genes that are really deep into the exon, maybe 200 base pairs, that have roughly a 17% probability, and this is pretty significant when you use this algorithm, anything that's greater than 15, that could be a cryptic splice site. So I think in cases where you don't really know, this just provides an additional tool that helps you, maybe focus on non-coding parts of the genome that might be relevant. And what we did was we ran this on the matched normals, and as well as developmental delay samples. We see some enrichment over here, but really it's not statistically significant. I look forward to when we can actually expand this and really start doing some burden tests to see if there's an enrichment of some of this signal in genes that might be relevant for certain phenotypes. So just to conclude, I hope I've given you a taste of the different operational concerns that need to be thought of as we set up a fully functioning and connected learning health system. And behind the scenes, to really make sure that that really flows, there is a lot of work in terms of the back-end informatics. And Illumina actually does have some capabilities, and we will work with you. We will bring partners along with us to help initiatives like the Taiwanese initiative to really help accelerate their path towards creating a learning health system. And with that, I'm going to hand it over to Xavier, who's